Any questions? Probably that means there are lots of questions. Because there's a 0-1 law. There's a 0-1 law for questions, I think. Everyone familiar with probability theory? Do you know what the 0-1 law is? Okay, well, it says that typically a probability is either 0 or 1. Please remind me of your name. Dilla. So let me just run through quickly. Husam Anjum. Abigail Arsenault. Thank you. Alexander Bullen. Jingquan Kao. Thank you. Jack Cerrone. Oh, thank you. Quan Jia Chen. Yuja Cheng. Thank you. Carissa Choli. Thank you. Arkapava Chaudhuri. Chaudhuri. Siddharth Dagar. Daniel Dima. Thank you. Emil Fedfeld. Justin Futh. Babek Germame. Thank you. Is it Germame or just Germain? Oh, okay. Charles Griffin. Thank you. Tenmei Goller. Thank you. Henry Hu. Zhao Hua Huang. Thank you. Java Kassan. Thank you. Alexander Cole. Zhao Cheng Lin. Yuan Yi Loken. Yifei Lu. Luke McCutcheon. Thank you. Abu Mohidin. Thank you. Ruben Navasarjan. Jonathan Ng. Thank you. Rishi Prakash. Thank you. Syed Mohammed Raza. H.Y. Shi. Lawrence Tsai. Thank you. Elin Wang. Thank you. Hongbo Wang. Xiaodong Wei. Chikam Wang. Oh, thank you. Okay. Oh, second part. Huyan Gujari. Oh, good. Oh, hi. Yeah. Yan Yi Zhou. He's in Ottawa, I believe. It could be on the, sometimes on the Zoom. Dailin Lee. Okay, well, one of the ideas in this course, well, why doesn't someone, does someone want to suggest what one of the ideas in the course is? Yes, Jack, what is one of the ideas in the course? Oh, okay, yeah. And don't forget, this is K theory. Linear algebra is K theory. right? But Abu, no, that, no, you're so. Please remind me of your name. I'm sorry. Akaprava. Okay, uh, um, I get a boost when I call it out and someone answers, but I guess you just came, you just arrived. So, yeah, good. Um, so Arkaprava, what is the main fact? What's the way of stating the main fact in linear algebra, which is closest to this course? Well, okay. Okay, yeah, right. Okay, have a base, have a unique basis, unique cardinality in the basis choices. But um, and how is that related to the course? Yes. Okay. Good. Okay. But you're making a bit of a song and dance out of it, which is good. Okay. No, this is very good. But there's also a one word. There's a one word um, way of connecting the two. Okay. One word. One letter. One yes. Um, Lawrence. Okay. Larry or Lawrence. Okay. Yeah. Oh. Okay. So what's the one word? One letter. What's the one letter? How does I come in? Capital I or small I? How does that come in? Oh, okay. All right. Good. Okay. Good. But um, what I'm thinking of is two choices for the single letter, either K or Z. Okay. How does that sound? Yeah, that's the acapella. Yeah. Right. And what about the converse? Suppose you just assume that Z. Assume that K0, however it's defined, well, properly defined, of a field is Z. Suppose you, as a group, okay, but with no semigroup in sight. Can you prove can you prove the semigroup is what you were going to say, or what you were saying? That's an exercise I've been jumping up and down on, and I just sent an email right now, by the way, uh, pointing out to people that if they want, they could do one every week. They could do one less of the exercises that Mr. Lau is proposing from the book. You know, his judgment for choosing exercises is extremely good. Okay, anyone want to know why? Anyone want to know why or how? How he got such good judgment? Yes. Yes. Yeah. Okay. How did you know? Oh, yeah, I see. Right. Okay. Okay. Good. So I guess he's in as good a position as anyone to suggest individual problems. Of course, he would choose the ones he found the most difficult, right? Okay, but then um, what I'm suggesting is that you, instead of uh, one of the ones in between difficulty, or maybe even one of the easy ones if you want to make life more interesting, instead of do one of the ones that come up in class. Like for instance, assume that K1, you're talking about a field, and that K0 group is isomorphic as a group, just as an abelian group, to the group of integers Z. Okay, and can you prove from that? Can you prove the basic fact of linear algebra in the form that the semigroup, what I like to think of as the Murray von Neumann semigroup, is of isomorphism classes in Larry's approach of finitely generated vector spaces, but that semigroup is just Z plus. Okay, once you know that, then you can prove that every basis, every finite basis for a vector space, a fixed vector space, has the same number of elements. Okay, and they should, but that's a good exercise too. Okay, so the whole business of of linear algebra as a spin-off from this course, if you like. That would be good for either extended exercise or so we figured that there's 14 times 13 different sections for the exercise, right? Because it's ordered pairs. A implies B, where A and B are arbitrary fundamental facts in linear algebra. So of course, what you do is you just stick a pin in. You write them all down. You could just do it, imagine them all, and you stick a pin and pick out one, and do that, and then maybe do the implications both directions on that one, because one of them might be easier than the other. Okay, so that's always fun if you want to prove two things are equivalent. Then as a warm-up, you try and choose which is the easiest implication, which is the easier of the two implications. Usually they're not equally difficult. Have I told the story about Elliott epoch-making paper which proved classification for amenable Feynman algebras? Okay, so it was that every amenable 2-1 factor, that's a Feynman algebra with a trace, of course not finite dimensional, and a unique trace. Every 2-1 factor which is amenable in the sense of an amenable group, don't worry too much what that is at the moment, is approximately finite dimensional. You can approximate it by finite dimensional subalgebras in a natural way, very natural way. Okay, so this had been open for well over over 50 years, open for 50 years from the time of Murray and Feynman. So but okay, so what he did is introduce a lot of new properties. Okay, because he wanted to do a tour de force. Well, that's the only way he could prove the term. But I'm giving away too much from the story. Okay, so he had property number 1, which was approximately finite dimensional. Okay, that was what he wanted to end up with, but he started with it. So that implies property number 2. That was easy. Property number 2 implies number 3. That's easy. Goes all the way down the list. I forget how many there were in this epoch-making paper. Okay, that's terrible. I shouldn't. So sometimes I say 7, sometimes I say 14. But it gets all the way down to the end. Okay, easy all the way. And then he says, well, now it's a difficult step to get from the end back to the beginning. That's difficult. But he's French, right? And the French have their own sense of humor. So he, in the paper, you can look it up. He proves number 14, if that's what it is. Number 14 implies number 13, difficult. Number 13 implies number 12, difficult. Number 12 implies number 11. Okay, and now all the way back down to number 1. Okay, that's how it goes. So, and my point is that that's a good example of implications where one direction is easier than the other. Two equivalent statements. Well, I'll repeat the name of the author. That's the same as the author of this fat book I'm carrying around all the time. Okay, Alain Connes, Connes, and it's you know I'm quite proud to mention that paper was published, a paper of mine for doing classification for AF algebras, sort of the first step in classification of amenable C-sphere algebras, was published. Both papers were published in the same year, 1976. And there was also another important paper in operator algebras published by in that same year, 1976, by Brown, Douglas, and Fillmore. Fillmore being a Canadian mathematician at Dalhousie University, and Brown being at Purdue University, and Ron Douglas um, having recently died, but he was at Stony Brook and then at Texas A&M as senior administrator. Well, okay, so that's, I'm suggesting that you it would be good to do to work over the relationship between linear algebra and K theory, and also and in particular prove that if you just know what the K0 of a field is as a group, then you can deduce, you can get back to more familiar territory by establishing what the deducing what the semigroup is. Okay, and another exercise which I summarized again in my email is the circle of ideas involving UHF algebras, and so and it really is a circle. Supernat, the category of supernatural numbers, which form a Cantor set, by the way. Okay, should be a natural part of the exercise. And then from there to the UHF. Okay, so these are all categories. From here to subgroups of the group of rational numbers containing the integers. Okay, and then the functor from here back again to here. Okay, so these are three categories. They happen to be sets. So as it happens, the first two and the last two, it makes sense to say they're isomorphic because they're set. Set by ejection. You have a set by ejection between them, preserving arrows. And the arrows, what are the arrows in supernat? Daniel, do you remember what the arrows are in supernat? Yeah, they have two. Suppose you have two supernatural numbers n and n prime. Then how many arrows can you have between them? Sorry? Right. So there might be one arrow, or there might be we might have an arrow in both directions, which means they would be equal. That's what isomorphic would mean. Okay. But you might have an arrow in just one direction, or you might not have any arrows at all. Yeah. Okay, so that's what that category is. And this category of subgroups of Q containing the integers, that's maybe even simpler to think of, because it's just a bunch of subgroups, and you assume that the integers are contained in them. But then if you have subsets of a set, that's a subcategory, right? That's a category because you can talk about inclusion. But you have to check that those arrows are associative. Okay, it's a category, right? Okay, and then you have functors, maps which preserve which are homomorphisms from respect to the arrows. Okay, so arrows go into arrows, and composition of arrows goes into composition of arrows, and preserve in a way that preserves the composition. Just the way you have a map between two groups. Okay. Okay, so that's the Grimm classification term. Okay, as formulated by Dijksma. And that's and then Dijksma went farther. He said, look at these are unitary UHF algebras. Well, I didn't say what the morphisms were here. Anyone want to recall that? Yes, yes. So morphisms A to A prime taking a unit to the unit. And So so you have to construct, the assignment would be, it's an essay perhaps, to construct all of the arrows, all of the functors, construct all the functors, okay? And then, but then you're finished, because if you have two UHF algebras and they give you the same, and they're isomorphic, then they have the same supernatural number, which means that the, and that which goes into the construction, right? So you have two UHF algebras, they come from supernatural numbers. And what this does, you have to say, if you have to say that they're going forwards and then coming back, okay? That's the same, that's equal to the identity. It's equal to the identity here. So you start with a supernatural number, you construct the UHF algebra, you go down to the subgroup, and then that's important how you get that. That was Dixbier's trick, going cleaning up what Grimm did, okay, simplifying what Grimm did. He got and talking about the subgroup. That's Dixbier's trick. But once you have that, then it's just number theory, completely elementary number theory to get a supernatural number. And it turns out that if you wanted this functor does have the property it takes n to m sub n, and then the n, this mn goes into 1 over n times z, and then this goes back to n. So that's the Grimm theorem. So this would be a nice essay, I think. And that's before we even talk about the non-unital case. So let's come back to the non-unital case later. So this is exercise 1. I'll call them 1E. I'll put an E after them to distinguish them from Mr. Lau's exercises. E for me. Yeah. Okay. And then exercise 2E is the non-unital case, okay? Then exercise 3E, that's the AF algebra case, okay? Which I'm going to talk about now. AF standing for approximately finite dimensional. So of course, a UHF algebra is approximately finite dimensional. Now, this approximately business in a purely algebraic setting that we've been talking about, there aren't any metrics, there aren't any approximations. What you say is that, well, it's algebraically, UHF is algebraically AF, meaning it's just a union of finite dimensional subalgebras, the increasing union of finite dimensional subalgebras. And that's what the AF algebras were. The algebraic AF algebras that we'll talk about will be the union of increasing sequence of finite dimensional, finite direct sums of full matrix algebras, okay, over the field. That, in this setting, it doesn't matter what the field is in the algebraic setting, as long as you do say it's full matrix algebra. Okay, so we did touch on the AF algebras last time. I don't know if this is going to last, this one piece of chalk is going to last all fall. Okay, this, I always am worried when I come into a room that has things on the blackboard, because I'm afraid that I'm afraid to erase it because it might be useful. Okay. Anyone see anything here that looks vaguely related? The circuit diagrams. Okay, here's a circuit diagram. Yeah. must have been a computer science meeting here, this room. If that's the closest thing I can think of in this building. But I didn't think that computer science dealt with actual down-to-earth electrical circuits. When I was about 9 years old, I had a piece of fiberboard which came in a set called Brainiac, and you could wire up various following recipes in the set. You could wire up various little things, circuits with light bulbs and stuff. It was quite fun. Okay, that's how I got to be able to recognize electrical circuits. Well, a little later, I helped my father assemble a Heathkit amplifier. Okay, you can't get those anymore. But then later I assembled one myself. The difference was first one was tubes, and the later one was transistors. Of course, it didn't make any difference to me. I had just working with the soldering iron and the pliers. Okay. The first one is not operational anymore, but the second amplifier still is. So I had an accident with it. The FM section for the tuner, radio tuner, is very delicate. You were warned about that. But where you move the dial for the side back and forth with the tuning to a station, there were a lot of light bulbs inside, and a couple of them, or one or two of them, were burned out. So I was sort of kicking the so I knew that would put the light back on again. So it did, but it blew out the FM receiver. Okay. But so I have a record player. I have a lot of records too, so it's good. Almost good. Almost good. Yeah. And anyway, I mostly listen to the radio on my telephone now anyway, because it used to be on the television, but the latest upgrade of the television system doesn't include the CBS classical radio. Okay, so what we want to talk about is what I'm suggesting we talk about now is sequences. Maybe we might as well assume they're increasing. Sequences of finite dimensional algebras, which are finite direct sums of matrix algebras over the field. It may as well be the complex number. So for UHF algebra, remember we could just draw a single point at each stage to represent the matrix algebra. The spectrum of the algebra would be a single point. And here, if it's a finite direct sum of full matrix algebras, and the spectrum is the union of the points. Don't worry what the spectrum is. This is just a schematic description of the representation of a finite dimensional algebra. So you have this going to another one, going to another one, and so on. And these are different dots. Okay. All right, and then going into A. Well, you can't draw this one schematically, as far as I know. In the article in the AMS notices once about 2-1 factors that I was mentioning a while ago, Vaughan Jones, the late Vaughan Jones, drew a nice picture of a 2-1 factor. Okay, so this is a finite type 1 factor. That's what a full matrix algebra is. Finite type 1 factor. Type 2 factor means that has a trace. Okay, I mean it has infinite dimensional, but it does have a trace. Okay, so well, this has lots of traces if it's unital. what anyway what Vaughan drew with the circle. Okay, in other words, it's a black box, a black hole, black hole. That's the 2-1 factor, and that was really quite accurate for his work that he was just talking about, because what Kahn proved with this epoch-making theorem was that if you have a factor, a subalgebra of a 2-1 factor, which is also a factor, okay, then it's the same one. It's isomorphic to the big one. If in this amenable case, okay, in the amenable or approximately finite dimensional case, the subalgebra subfactor is always the same. But what Vaughan Jones set out to do then was look at how many different ways you could have this unique subfactor embedded in the big one, okay? And somehow, working with this, he discovered what's now referred to as the Jones knot polynomial. And one thing led to another. In particular, there was considered a field metal work. And also for Witten, who adapted gave an explanation for this invariant in terms of quantum field theory. I guess I was describing that one day. Well, okay, and these knot polynomials are really useful because you could tell the difference between the knot tying up your left shoe and the knot tying up your right shoe. Okay, the mirror images of each other, presumably. We're consistent. That's how it should go, right? All right, but so we're talking about maybe it's called A. We can think of it as the maybe the so the Lehmann algebra one should be a solid black. Maybe the C-star algebra one could just be like a newspaper black, just a whole lot of dots. Okay, and what we want to do is classify these in the same way that try to classify them in the same way that UHF algebras are classified. But those, the isomorphism classes, are just the Cantor set, right? The supernatural numbers. They parameterize the isomorphism classes of UHF algebras. Now, when you go to the free floating algebras, which is what I meant by the non-unital case, okay? Dixmay did another non-unital case too. But you go to the free floating algebras, then the isomorphism classes are a little more complicated. You have to look at when two supernatural numbers give you the same floating algebra. You have the two algebras, Mn and Mn prime, okay? But then you let them float, meaning you put them inside infinite matrices. There's only finitely many non-zero. Only finitely many non-zero entries, so you can add and multiply them. We can always add them, but multiplying is a problem in general. If you don't look at the general case. If you look at the norm completion, then it's you have all the entries non-zero, but that's matrices aren't necessarily the way to look at it then. Okay, but so that's a good exercise too. That's the non-unital case. How do you decide when the two supernatural numbers? This came up last time, I think. So when do this free floating algebras give you the same? So Mn and M prime, free floaters. They're isomorphic is equivalent to what relationship to n is equivalent to n prime how, okay? That's the exercise. It's an equivalence relation between n and m prime, but the free floating algebras, infinite matrix algebras, are isomorphic as algebras. And of course, no unit gets preserved because we're not, you can't, it's cheating to keep track of the matrix description, okay, when you're looking at the abstract algebra. But there's a very simple relationship between n and n prime. But yes, remind me of your name. I know it, but Vincent, yeah. And okay, but are you remembering from a previous discussion? Which algebra?
2-1 algebra.
Okay, but I didn't even mention that term, right? Okay, so that means you've been looking into it already by yourself. Yeah, good. All right, maybe you can tell us. Well, no, look, type 2 means that if it's 2-1, then that means it's infinite dimensional. Okay, so if it's 1 sub n where n is finite, Roman numeral 1 sub n where n is finite, that's n by n matrices. Okay, and if it's 1 sub infinity, then it's infinite matrices, but the matrix of a bounded operator. Okay, on L2 of the integer maybe. But if you're wondering what the 2-1 factor is, well, to get an example, you may have you could think about it, okay? But Murray and von Neumann, when they were introducing these, they first defined them before they knew there were any, and after a while they found some. You might see if you can find one without looking it up. But that means it has a trace and it's infinite dimensional. Okay, and it's and you can't break it up as the sum of two others. Like if you look at L infinity of the interval, then you can break that up as the sum of L infinity of the first half interval and the second half interval. But that does have a trace. Infinite dimensional, it has a trace, namely just the Lebesgue integral. Okay, not unique. So anyway, but the point is, how do you get such a 2-1 factor? And it turns out that you can get them from a UHF algebra. Okay, and that's where Kahn sort of, that's what he was proving, that an arbitrary immutable one comes from a UHF algebra in a natural way. So you can take a look at that, see if you can formulate that. But there are other constructions too, completely independently of a UHF algebra. Well, okay, so the question is, the next question to look at is if you have two AF algebras, A and A prime, then they're saying they're isomorphic is equivalent to what? Okay. Well, in one direction is easy, okay? It's easy because we know what functors are, right? And the functor is something that takes any two isomorphic objects into isomorphic objects, right? Okay. So what's our favorite functor? Yeah. Okay. So take this is certainly implies that K naught A is isomorphic to K naught A prime, and even as order groups. Okay. Order group means it's the enveloping group of a semigroup, which it is. The semigroups would be the positive cone, positive element. So order, if it's an order group, we only have to know when something is positive, because then something in general is less than or equal to something else. Charlie, do you know what that means in terms of the positive cone? You add something positive to something, you do anything, you get something larger, right? Okay, well, that's the definition of the order structure. So for order group, you only have to know what the positive elements are. Sometimes it's called a partially ordered group, but the way I look at it, if someone wants a group to be totally ordered, they'll say so. Okay? And there are a lot of other terms like pre-ordered and subgroup, ordered subgroup, so suborder group. And if you have to add the word partially, it very quickly becomes unwieldy. So I'm anyway, when I was in first year, Queen, maybe it was second year by that time in those days, I learned that you had two kinds of relations, two kinds of fundamental relations in mathematics: equivalence relations and order relations. Okay, and they each had three axioms. Each had three. I can't quite hold it. Okay, three axioms. Okay, axiom one is the same for both. Everyone remember that? Well, just think about it. Axiom 2 is the same for both, exactly the same. Axiom 3 is opposite. Okay, one of them is symmetric, one of them is anti-symmetric. Okay? And furthermore, you can go farther because if you have the first two, that's called a pre-order group. But then if you symmetrize it, you say something is related, x is related to y. If x is less than or equal to y, and y is less than or equal to x, okay? Then look past, that's an equivalence relation, and it's an arbitrary equivalence relation. And you pass to the quotient. And that's an order relation now on the quotient. And actually, I'm sorry, that's not an arbitrary. Before you pass to the quotient, it's not. Or if you look at the quotient, it's an order relation. It's saying that the symmetrizing is not arbitrary order, not an arbitrary equivalence relation, because you know, I'll have to think about that. But anyway, but this is a really fundamental language in mathematics. Okay, it's you have a pre-ordered pre-order relation, then it gives you both an equivalence relation, which I think is, it can be said as being arbitrary, and then the quotient of equivalence classes give you an order relation, which is also arbitrary. And I don't know what started me on that, except every once in a while someone corrects me. If they, according to their lexicon, that they say you should say partially ordered. And I'm tempted to say if I want it to be totally ordered, I'll say so. But I may not even say so. It's irrelevant in a sense. Okay, but now I'm stalling because I'm waiting for someone to talk about the converse, right? The converse is the classification theorem. It says that the functor on the category of AF algebras, say stable AF algebras, free floating. You take a given AF algebra and you float it, okay? Put it into infinite matrices. And the K0 group will be the same. But now if it had a unit, there's no special unit, no special element of the K0 group. So it's just an ordered group. Okay. And all right, so it's not only a functor. What kind of a functor is it? Abigail? Yeah, classification functor. This is you know, you can tell when I start to wake up, that's where I come in. That's my cue, okay? That's what I like to talk about. I mean, it's not. I guess I could learn to talk about other things too, but it turns out that it's pretty hard to talk about anything. You know, this is my worldview. It's pretty hard to talk about anything which is not rather closely related to classification theory, one way or another. So, but by the way, I read just a non-C-star algebra source that the main purpose of the main function of the human brain is to sort things, classify. Okay. Usually in a good way, useful way, important way. Okay, so the converse is a classification function. And, now, in the UHF setting, the proof, by the way, will be quite similar to the non-unital UHF setting, the free-floating UHF algebras. If you can do those, then it'll be somewhat similar. Well, I'm speaking too soon, maybe, but let me give you a short proof, summary of the proof, okay? Quickly. Proof that if the K zeros are order isomorphic is order group, then the algebras are isomorphic. Okay, you look at A1, A2, and so on, and you look at A1 prime, A2 prime, so on, prime, and you look at the K groups. And by the way, the K0 preserves the limits, okay? So and then you assume that there's an isomorphism between the K groups of A and A prime. So the first step is you pull it back to an intertwining, okay? Of the K0 groups, of the finite stage K0 groups. You have to pass the subsequence. This is the first step. The second step is each one of these up-down maps, down or up maps, there's an algebra map. There's an algebra map that gives rise to it, okay? But it's not unique, okay? It's not unique. That's the second step. And you choose algebra maps to give you the K0 map. And for that, you don't have to pass to a subsequence. And at least if these are unital, if it's unital, and the unit gets preserved. Okay. Well, then the third step is you modify. You're always free to modify any one of these maps by an in or automorphism. Okay. So you do that using a uniqueness theory. This was existence. You get the individual ups and downs, but to get the commutativity of the little triangles, you use uniqueness. The across and down up are two maps between A1 and A2. They agree on K0, so therefore they're unitarily equivalent. And the second triangle, you look at the new first, composing the whole up, down, up by with a single unitary, just changes this second arrow. Okay, so then you look at the second, so you don't change the first arrow, and then you look at this second triangle, and you go up with the revised up arrow, and you go down, up, down, and across. Those are unitarily equivalent. You put in the second unitary, and you're not changing the first. That only affects the second arrow, the third arrow. It doesn't affect the up arrow. You just keep on going. That's the proof, okay? So the third step was this was the third step. Three zigzag steps, and at the end you're finished because you have a commutative diagram of homomorphism. It passes to it's elementary, immediate. It passes to an isomorphism in the limit. Okay, which is what we were looking for. And okay, the only trouble with this, the reason I'm somewhat hesitant, I had to think twice before burdening you with this, especially overtime. The last time I did this at a meeting, not a class meeting, but an international meeting. The late Professor William B. Arberson who has always been a supporter of mine, had always been a supporter of mine up to that point. He came up to me after the lecture and he said, if you do that again, I'm going to walk out. Okay. All right. So well, there's no, it doesn't look as if there's anyone coming in right away. Well, but I think maybe there's not, will be. And, but we can talk, anyone that has a few minutes and wants to talk for a bit, we can do that outside.